Ladies and gentlemen, it seems that we are about ready to begin the final session, final keynote speaker in this conference. In 1985, this university celebrated its 60th anniversary. And for that anniversary, the university invited several honorary doctors. President Koivisto, the President of Finland, was one of those, and as well as Professor C.R. Rao from the Indian Statistical Institute and the University of Pittsburgh, United States. When we made the proposal of his honorary doctorship, we had to tell that why we wanted to invite him as an honorary doctor, and what we did. We came to the administrators of this university the resume of Dr. C.R. Rao. And what they said, please say that in one sentence. And that's not a very simple task. And we worked very hard and tried to tell them why we wanted to do that, and the result was as follows. We proposed the honorary doctorship to Professor Rao because of his great scientific contributions and merits in the promotion of research in the University of Tampere. It is my honor and the greatest pleasure to give the floor to Dr. Rao, Doctor of Philosophy and National Professor in India. Professor Rao.
Thank you. Since this is the last session of the conference, I would like to have your permission to thank Professor Pukkila and all his associates for organizing this conference, inviting many experts, and giving us an opportunity to learn about the current research in mathematical statistics, especially in linear models. I had the opportunity to attend the first Tampere conference. No doubt the second one is much bigger in terms of the academic program and the number of delegates attending the conference. The organization of a conference of this magnitude is not an easy task. Professor Pukkila and his associates have done very hard work. They will be relieved to know that both the academic program and the social programs were excellent, and we are looking forward to a third conference in Tampere. When I came to the university on Wednesday morning to attend the conference, the first thing I noticed was a poster containing the sketches of the keynote speakers. I was surprised to see that poster. Whenever I used to see posters of Gauss and Euler, I was fondly hoping that 200 years from now, somebody will make a poster of me. I was surprised that during my lifetime, this hope was realized. Anyway, it is a very nice and a kind idea conceived by the organizers and very beautifully executed by the artist Kalevi Kankala. So I would like you to convey our thanks to the artist, and I would like all of you to join with me in showing our appreciation to Professor Pukkila and his colleagues in the usual way. Today I would like to talk to you about estimation in linear models with mixed effects. I would like to present to you a unified account of this problem and then give you specific examples. Although the examples I will give you are ones which are already published in my papers, I never thought of the unified theory before I worked out a few special examples. Now the unified theory which I am going to present to you is, I believe, new. The problem of a mixed model is stated in the usual way. We have x beta plus u times psi plus epsilon. Epsilon has the variance covariance matrix sigma. Beta is a fixed parameter, vector parameter, but psi is a random variable. Expected psi is a times gamma. Gamma is a fixed parameter, and it has a variance covariance matrix gamma, and it's uncorrelated with the error term epsilon. Now our problem is to estimate a linear function of the fixed parameters and a linear function of the random variable psi by a linear function of the observed variables y, a plus L prime y. Now what is the criteria of estimation? We will, as in the case of fixed parameter, we will say the expectation is 0 independently of gamma and beta, and the mean square error is a minimum, the expected mean square error. Now as in the case of the fixed parameter, we have a condition of this kind, that the P and Q must satisfy these conditions. In other words, that this vector P, A prime Q, must belong to the column space of this matrix over here. And once this necessary condition is satisfied, we can compute the expected mean square error, and it comes out to be in this form, where G is the matrix sigma plus u gamma u prime. So we have to minimize this quadratic form over here subject to this condition. And it turns out that let's remember that we wanted a linear function a plus L prime y to estimate the parameter, to estimate the function p prime beta plus q prime psi, and it turns out that L satisfies this equation, and G is of the form sigma plus u gamma u prime, where x is S is this matrix and small s is this vector. We notice that we assume that the random variable psi has an expectation a times gamma. Actually, you can transfer that fixed part in psi to this design matrix over there, and take the expectation of psi to be 0. So we can rewrite the model in this form, x star delta plus zeta, where zeta has this variance covariance matrix. And now expected value of eta is 0. Now where did the unification come in? Now in the case of linear model with fixed effects, now this kind of matrix played an important role. So we have a partition matrix here. G is a non-negative definite matrix, and S is the design matrix. Let us take any generalized inverse of this matrix. Then the optimum L is given by the sum of these two expressions, where C1, C2, C3, C4 are the elements of the inverse of the partition matrix over there. Now it's exactly the same matrix which appears in the theory of linear models with fixed effects. In that case, G was simply the variance covariance matrix of the error term, which is sigma. Now it is sigma plus u gamma u prime. There is an additional non-negative definite matrix which comes in G, but the arithmetical operation is exactly the same. Now what's the advantage? Once you compute the generalized inverse of a partition matrix on which considerable work has been done, then it solves all our problems. Now, we can write the partition matrix by splitting C2 into two parts over there. And then we notice that how do you estimate the fixed effects? Beta hat is C prime beta times y. Now, how do you estimate the fixed gamma effects? So, once you have this matrix, that will give you whatever we want. And how do we estimate the eta, the random variable, which is psi minus this? So, it's given by this matrix. Now, how do we estimate the sum of these two, which is given by this expression over here? So, the unification comes through the computation of the generalized inverse of this partition matrix. Now, what is more important is, as I said, we could estimate p prime beta. Suppose we want to estimate only p prime beta. It's estimated by p prime beta hat, and its mean square error is given by this. And where do we get this matrix? It's over here. And suppose we want to estimate a linear function of gamma, the other fixed effects, then the mean square error of this, there should be 2 over here, and the expression is here. And where do we find C gamma gamma? It's over here. And similarly, if we want to find the estimate of the linear function of the fixed parts, then again we have here, where is C4? C4 is over here. So, the estimates as well as the expressions of the mean squares are all contained in the generalized inverse of a partition matrix. Now, this was the result which I proved long ago in the case of fixed effects model. Now, we find the same holds in the case of a mixed effects model. Now, what about the estimation of psi? So, we notice that if you want to predict a linear function of the random variable psi, that is given by this, and the mean square error is again involves the elements of the partition matrix. Now, it involves both C gamma gamma and C gamma. And finally, this is what we wanted to estimate. So, we have we simply substitute for beta and psi the estimates beta hat and psi hat, and the mean square error involves again the elements of the inverse partition matrix. So, the key to estimation in mixed model is the computation of the inverse of a partition matrix, which is a symmetric matrix. And once we compute the inverse of that matrix, we can write down the estimates of all functions of the fixed parameter and the random effects, and also get expressions for the mean square errors of the estimates. Now, we may ask, we have to estimate gamma and sigma. These are unknown. Let's see, what are the unknown elements here? Gamma, the lowercase gamma, which is the expectation of psi, which is involved in the expectation of psi, and capital gamma, which is the variance covariance matrix of psi, and sigma, which is the variance covariance matrix of the other term. Now, we notice that by taking away the fixed part, we can write the model in this form, where the covariance matrix of zeta is of this form. So, it is reduced to the problem of the estimation of the variance covariance components in the ordinary fixed effects linear model. Well, we could use some of the well-known results in the estimation of the variance and covariance components to find estimates of gamma and sigma, and use these estimates in the expressions which we already have for the estimates of the linear combinations of the fixed effects and the random effects. What I propose to do is to consider some special cases where we could estimate gamma and sigma in a very simple way and establish their optimum properties. Now, the first one is an example which I worked out some years ago, but I like this example, so I want to show it to you once more. Now, here the problem is we have k linear models, yi is u times psi I plus epsilon, and psi I is a vector. And we want to estimate psi 1, psi 2, psi k. Well, the problem may be given to us as the estimation of fixed effects. But when we think of k-linear models, we can always think of a population of the values of psi from which these linear models arise. It's a natural way of looking at the problem. So we can interpret this model as k fixed effects model, or it is a random effects model where we have a sample of k psi values. If you look at this model in this way, there are some advantages. Now first, if you take the view that they are all fixed effects models, k in number, then we can compute the least square estimate of psi in the usual way from the Gauss-Markov theorem. And it will have this property that the expected value, the least square estimator naturally given the parameter is psi is unbiased, and it has a variance covariance matrix sigma square W, where W is this matrix over there. That's the well-known Gauss-Markov theorem. Now, the advantage of looking at these models as random samples from a population of models is because we could use what is called the empirical Bayes theorem, where we could now assume that expected value of psi I is gamma, and it's capital gamma, and this is so. And from this expression that both psi I and yi has a variance covariance matrix, you can find the regression of psi on y, because y is observed, psi is unobserved hypothetical variable. The regression of psi on y is exactly this one. Now, this is what comes out from the estimation of random effects from the general theory, and it turns out that when you look upon psi as a random variable, it's a function of the least square estimator of this type. You subtract from the least square estimator at constant times this value or that. In other words, you are drawing the least square estimators towards the mean of the values of the psi. A sort of a kind of correction to this. So the advantage of this is, when you want to minimize the mean square error of estimation over a population of values of psi, that's over the a priori distribution of psi, you have a minimum. And now this involves some unknown parameters like gamma and sigma square, and we notice that yi, if psi is a random variable, yi has this distribution, and you can estimate gamma, capital gamma and sigma square from the joint distribution of y1, y2, yk by using some method like maximum likelihood. Now, I write again the Bayes estimator of psi in this form. Of course, a true Bayesian would probably make an assumption on little gamma and capital gamma and sigma square, and he is through. But in our case, since we have, so to say, a sample of size, we can make an estimate of the prior distribution. That's how the empirical prior distribution comes in. And this is the way you estimate gamma as the mean of the size, and sigma square and this. And we can write down the estimate. Let's notice this is the estimate over here, and sigma square is estimated by S, so to say, and this is estimated by B minus 1. Now, B is an unbiased estimate of gamma plus sigma square W. But when you take the reciprocal, the inverse of that matrix, B minus 1
the expectation of that is not exactly this, but it's a constant times this. So in order to make a correction for that, you write the estimate in this form. You see that you are making little refinements over here. In the general theory, I said we have an expression for the estimate of the random variable, and it involves some unknown parameters. We estimate the unknown parameters and substitute for the unknowns the estimates. But here we are trying to make little refinements by writing the estimate in this form. And then I compute the mean dispersion error, and it comes out in this form because now it will involve C. Now I choose C such that the mean dispersion error is a minimum, and the choice of C turns out to be this quantity over here. This is a little innovation, that you write the estimates in this form and determine C such that it has the smallest dispersion error. So we have this. The total dispersion error is minimum when you choose C. So what's the estimate? The empirical base estimate is this minus, for C you write this quantity and write down this. Now we have this interesting property that this empirical base estimator of the random effect psi 1, psi 2, psi k is not unbiased for the given value of psi I. We notice that the least square estimator is unbiased, but the empirical estimator is not unbiased for psi I. However, it has the smallest mean dispersion error. That is true in the case of regression problems. And it may also happen that when you are estimating psi 1, psi 2, psi k by empirical base estimator, that you cannot guarantee that for each I, the empirical base estimator has smaller dispersion error than the least square estimator. But what is true is, if you take the summation over all I, now that is smaller than the summation of this over all I. So some random variables are predicted with greater precision than other variables in such a way that the sum here is smaller than the sum, but individually it may not be so. So some estimates have greater error than other estimates. So that's an interesting property of these estimators. Now it may also, we could, in my previous case I assumed that all UIs are the same, and now we can think of different design matrices. The estimation is again the same. This is the base estimator. It's easy to write down from the general theory, and the unknowns are sigma, square, and gamma. Now here I propose a method of estimation for sigma, square, and gamma. These are not maximum likelihood estimators. In the case where all UI are the same, we have nice maximum likelihood estimators for sigma, square, and gamma. But now these are some kind of ad hoc estimators which coincide with the maximum likelihood estimators when all the UIs are the same. So if all the UIs are not violently different from each other, this kind of simple estimators might be sufficient to give reasonably good estimators, empirical estimators of these psi variables. We could also introduce into this model some fixed components like xi beta. Now these models are very important in biology, especially in genetics, where the component psi I is called the breeding ability of an individual, and these are some concomitant variables. And in genetics, the problem is the prediction of these variables I. So you notice that it is a mixed effects model, but we have repetitions of that model. So we could do it in the same way from the general theory. We obtain the estimates of psi I beta in this form, where eta I beta is equal to this. So first we estimate delta and then write down the regression of eta on y, and it comes out to be in this form. And again, the unknown elements are sigma square and now this is a problem which you may like to look at and see what is the proper solution to this. I have random variables psi I, which have a distribution of this type with expected value of this, and the mean value is and the variance covariance matrix is this. We have an independent estimate of sigma square available, because each model will give an estimate of sigma square. And now how to find the estimate of gamma, small gamma and capital gamma from variables of this kind? When all Wi are the same, that is when all the design matrices are the same, then the answer is simple. But when they are not the same, it is very complicated to obtain the estimates of gamma and capital gamma. So I give here some method of doing that. You notice that it involves some complicated matrices. So as soon as the balance is violated, you get into complicated arithmetic. So however, we can find some kind of estimates of small gamma and capital gamma by considering a linear model of this kind, which involves all the design matrices, and we estimate in the usual way. So I skip this. Is finally you obtain an equation which gives us an estimate of gamma, and sigma square is all. With the estimate of sigma square is already known. Therefore, we can estimate gamma. Now, this is a very, very special case where which occurs in genetic selection. So, this is a scalar variable, and this is the breeding quality of an animal, and these are some concomitant variables, and we have repetitions of this measurement n times, and we have k animals I1 to k, and we want to select the best among them. So we take the average, since there are ni repetitions of this model, of this equation. So we take the average and write down in this form. So we have k equations corresponding to the k animals, and these are the breeding qualities of these animals. So all these mean values are based on different numbers. There are samples available for these animals, and the model on the mean values can be written in this form. Now we see this is a mixed effects model. Therefore, we can use the general theory to estimate delta and eta. Now, the only problem here is how to estimate the variance of this breeding abilities and the variance due to the random error. So, sigma 1 square and sigma 2 square. So, this is again the variance components problem, and we have to estimate sigma 1 square and sigma 2 square. So, this is how it works out, and there are two equations which gives the values of sigma 1 square and sigma 2 square. And these sample sizes are different in this case. Now, if the sample sizes are all the same, then we have a very nice solution.
So we write the vector of the breeding abilities, and the estimate in this form, and here the unknown sigma square and sigma 2 square are involved. So you minimize the mean dispersion error, and you can find a C which minimizes the mean dispersion error, and giving the compound mean square error of prediction in this form. So we have very nice solutions when it's a balanced case, and solutions are not so nice where it is not balanced. Now finally, we have the multivariate model. Now there are lots of problems when we come to the multivariate case. I hope some of you would like to look at these problems. This is now a vector, and these are concomitant variables, and these are the regression coefficients, and this is again a vector of the breeding abilities, and that's a random error. This is an important case which was originally considered by Fisher and Fairfield Smith. Suppose you want to select a variety of wheat for high yielding quality. Now, the selection need not be based on the observed yield alone. It can be based on the observed yield and other characteristics of the plant. So that's how the multivariate case becomes very important. In other words, eventually the breeding quality of the animal is defined as a linear combination of these hypothetical quantities. Now the problem is how to estimate eta I from this. As before, we take there are repetitions of these observations. So we write the model in this form: xb plus eta plus epsilon, and these are the fixed effects, and these are the random effects, and that's the error. Now the only problem here is that so we can write it in this form: y equal to x beta plus zeta, where the zeta has the variance covariance matrix of this type. Now this is the multivariate linear model. Let's note that y equal to x beta plus zeta. Now if all the diagonal elements of this are the same, or in other words, if each row of this model has the same variance covariance matrix, then we have the simple estimation method for the multivariate linear model. Now, how do you estimate the fixed effects in a multivariate linear model when the error terms have different variance covariance matrices? Now, once we make these matrices different, the problem of estimation becomes somewhat complicated. I was surprised to find that these are not worked out in books on multivariate analysis. The estimation of the fixed effects when the error terms have different variance covariance matrices. But if you go through the algebra, you find that the columns of B, if you write it as beta 1, beta 2, beta p, these are the regression coefficients associated with different characteristics. Now they can be obtained as solutions of equations of this kind. In the usual multivariate model, it is simply x prime x beta is x prime y. So you solve for B easily. But in this case, you have to solve for the columns of the matrix B through complicated equations of this kind. Once you solve this for this matrix B, then you can estimate the breeding ability of the individual I by this formula, and we notice that sigma could be estimated to the repetitions of the observations on a given individual, so that's no problem. And then gamma is estimated by an equation of this kind. This is not a maximum likelihood equation, but it's a kind of ad hoc equation. And
using these two equations, we can estimate sigma and gamma. Now, when all the sample sizes are equal, we have a nice solution. And if all ni's are equal, you can estimate gamma, beta, and psi I in the usual form. And we can write, notice that this is the estimate of the breeding ability, and gamma and sigma are unknown, and they can be estimated through this matrix gamma over here, and we can write the estimate in this form, introducing a constant c, then there's a universal constant which minimizes the mean dispersion error, and we have a very nice solution in this case. But if the values of ni or sorry, that was the solution when sigma is known, but if sigma is not known, we can still write the estimate in this form, and this is the expression for the total dispersion error. Unfortunately, there is no universal constant c which minimizes this. The constant c which minimizes this involves the unknown parameters gamma and sigma. However, we can find some approximation to the true estimate, to the estimate which minimizes this expression, and obtain the total dispersion error in this form. Now, the effect of making this approximation, which is independent of gamma and sigma, is to introduce another expression over here, which shows the smaller order of magnitude. So, we then have some kind of satisfactory solutions to the problem of estimation of breeding qualities of individuals, which is an important problem in mathematical genetics. Thank you very much.